Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Silbershatz, Gagne, and Galvin, published by Wiley Publishing. In the last lesson, we were introduced to dynamic loading of a program or a process and dynamically linked libraries and how they are loaded and used. But I'm not sure I made clear what a DLL actually does. Dynamically linked libraries allow for the modular development of applications. For example, the various instructions necessary to control a printer are the same no matter what the application. So why have the programmer write the code to control a printer when it's possible to include that code in a library that can be called from the application? The same can be said for other examples, such as managing graphics or utilizing a graphical user interface and so on. An advantage of using dynamically linked libraries is that changes or updates to those libraries have no effect on the application programs that call them, unless, of course, the update has an error, in which case the error is isolated to the library code and not the application code. So dynamically linked libraries are a significant feature of memory management. Now let's move on to explore where a process is placed in memory. Main memory must accommodate both the operating system and the various user processes. Now we already know that. We therefore need to allocate main memory in the most efficient way possible. This section explains one of the early methods, contiguous memory allocation. So essentially what we're doing with this lesson is beginning our exploration of a number of different methods used to allocate memory to processes. The memory is usually divided into two partitions, one for the operating system and one for the user processes. We can place the operating system in either low memory addresses or high memory addresses. Low memory addresses is the memory at the beginning of the address space. Some processors use designated low memory addresses during power on, exception processing, interrupt processing, and other hardware conditions. Some operating systems use designated low memory addresses for global system variables or global system structures, jump tables, and other system purposes. However, a lot of operating systems, including Linux and Windows, place the operating system in high memory. We usually want several user processes to reside in memory at the same time, correct? We need, therefore, to consider how to allocate available memory to those processes that are waiting to be brought into memory. In contiguous memory allocation, each process is contained in a single section of memory that is contiguous to the section contained in the next process. In other words, in this scheme, each process is assigned to an available block of memory. The entire process that is loaded is limited to this block. You see, it cannot be stored partially in one block and partially in another. In other words, a process cannot be stored in memory locations that are separated from one another. Before discussing the memory allocation scheme further, though, we must address the issue of memory protection. We can prevent a process from accessing memory that it does not own by combining two ideas that we have already talked about. If we have a system with a relocation register together with a limit register, we accomplish our goal. The relocation register contains the value with the smallest physical address. The limit register contains the range of logical addresses. Each logical address must fall within the range specified by the limit register. The memory management unit maps the logical address dynamically by adding the value in the location register shown in this image. The mapped address is sent to memory. When the CPU scheduler selects a process for execution, the dispatcher loads the relocation registers and the limit registers with the correct values as part of the context switch that we talked about earlier. Because every address generated by the CPU is checked against these registers, we can protect both the operating system and other users' programs and data from being modified by this running process. The relocation register provides an effective way to allow the operating system size to change dynamically, which is desirable in many situations. For example, the operating system contains code and buffer space for device drivers. If a device driver is not currently in use, does it make sense to keep it in memory? Instead, it can be loaded into memory only when it's needed. Likewise, when the device driver is no longer needed, it can be removed and the memory allocated for other needs. Now let's talk about memory allocation. One of the simplest methods of allocating memory is to assign processes to variably sized partitions in memory, where each partition may contain exactly one process. In this variable partition scheme, the operating system keeps a table indicating which parts of memory are available and which are occupied, as you can see here. Initially, all of the memory that is not used by the operating system is available for user processes and is considered one large block of available memory. Eventually, as you will see, memory contains a set of blocks of various sizes. This figure that you see here depicts such a scene. Initially, the memory is fully utilized, containing processes 5, 8, and 2. After process 8 leaves, there is one contiguous block available. Later, process 9 arrives and is allocated memory, leaving us with a little bit smaller available block. Notice what would happen if process 5 leaves. There would be two non-contiguous blocks. One right here where process 5 was and the original block. We have two non-contiguous blocks. There's no problem with that if we have one or two smaller processes that need to run. But consider our predicament if the processes waiting are larger than either of those two blocks. We'll soon see how future evolutions of memory allocations take care of that. As a process enters the system, the operating system considers the memory requirements of each process and the amount of available memory space to determine which processes are allocated memory. When a process is allocated space, it is loaded into memory, where it can then compete for that CPU. When the process terminates, it releases its memory, which the operating system may then provide to some other process. This is beginning to sound like an old story for us, isn't it? What happens, though, when there isn't sufficient memory to satisfy the demands of an arriving process? One option is to simply reject the process and provide an appropriate error message. Doesn't sound like a very good option to me. Or we can place such processes in a wait queue. When memory is later released, the operating system checks the wait queue to determine if that memory will satisfy the memory demands of a waiting process. For example, consider our image. After process 5 has left, we have 9 and then 10 arrives. And we have 9 and 10. This graphic is not showing exactly what I'm saying, so listen to me. Process 5 leaves, so it's not there. Process 9 is there, and we have a contiguous block at the top, and we have this contiguous block down here at the bottom. Process 10 arrives, so now we have the operating system in this block, a blank block right here. 9 and 10 are occupying this one, and a blank block right here. Now that's a fairly small block, and so is that one. Now if either 9 or 10 will leave, well then we have at least one slightly larger block, and therefore something might fit it. In general, as I mentioned, the memory blocks available comprise a set of blocks of various sizes scattered throughout the memory. When a process arrives and needs memory, the system searches the set for a block that is large enough to hold this process. If the block is too large, it's split into two blocks. One block is allocated to the arriving process, and the other block is returned to the set of blocks. When a process terminates, it releases its block of memory, which is then placed back into the set of blocks. If a new block is adjacent to another block, these adjacent blocks are merged to form one larger block. Simple, isn't it? Let's take a break right here. I think that's a good introduction into contiguous memory. Go ahead and look over your notes, update your study guide, and when you're ready, come on back, and we will start talking about a topic, general dynamic storage allocation problem. See you in a bit.